Hey, welcome back. This is part 4 of building a neural network from scratch. And in this section, we're going to do backpropagation. Now, backpropagation is pretty easy, I think, to intuitively understand in the sense that we are just working our way backwards and we're going to be adjusting the weights in order to try to get the output to more closely match the expected output. So that being said, the intuitive part might make sense to you, but the actual math that we're going to do is a little bit complicated. And I'm not going to discuss it too much. I'm just going to kind of go through the code and get something that you can play with. And I'm going to skip over a few of the more mathematical technical parts that involve the chain rule and things like that. If you want to know more about that, look down in the description, and I highly recommend going through the 3 Blue 1 Brown video series on neural networks. It has everything on gradient descent and everything in there that you need to know in order to understand the underlying math for this process. Okay, but this tutorial is not really about the math, it's just about getting a working model to play with. So what we're going to do first is we're going to create a function called backpropagation. There we go. And what we're going to do is create a variable called error, and that error is just going to be the expected value minus what we got out for the output. So if I print this out, and I need to call this after I do my feed forward, what I get is this. So this is the error that I got based on what the expected value was and the actual value was. Now at the moment the error value can be positive or negative, and actually it doesn't really matter for this toy example, but most of the time people don't use this really simple method for error. They use something called mean squared error, or they use something else to run it through. I'm not going to run it through that for this. I'm just going to leave it as simple as possible. You could take the absolute value of this and do it just the same. I am not going to do that. I am just going to leave it just like this, and I've already tested it and it will work just like this just fine. Okay, so we're just going to take the error like that, and we're going to use this error and we're going to work our way backwards, and we're going to adjust the weights in section 2. Or really what we're going to do is find out how much to adjust the weights by. And to do that, I need to actually find the gradient based on the function that I used, which is the sigmoid in this case for activation. So why do I need the gradient? This is all getting to the gradient descent part, which I'm not going to go into detail on, but I will explain this to you. The activation, when we run it through, and the reason we run it through this sigmoid activation function is because when I find the derivative of the sigmoid, it produces a really nice function for us. And that function is just going to be x times 1 minus x. And this function, it's a really nice function in the fact that it's very simple and it's easy to compute. It doesn't require any special, square roots or anything like that. So it can make training a neural network go really, really fast. So why do we need the derivative? Well, the derivative is going to tell us the gradient based on what we passed into the activation function, which is going to be the values coming out of this weights here, where really the hidden layer times the weights gives us that value that's passed into activation. And then based on the output here, we can use that to tell us how much we need to adjust the weights here by. So if the gradient's really high, if it's a really large gradient, really low gradient, that tells us how close we are to kind of finding the optimal values for those weights to get this output down to 0 error. So if we have a really high error value, we want to adjust that by a larger amount. We want to adjust the weight more in order to get the output closer to the expected value. So if it's a really low error value, then we know we're already really close, which means that gradient is going to be closer to, well, it's going to be less of a gradient. It's going to be closer to just a flat line sitting there at the bottom of some curve or something like that. If you want to look at kind of the intuition behind gradient descent, go look at some 2D examples, which will show a nice little curve and then the gradient slowly getting close to the bottom of that curve. And hopefully that will help gain a little more intuition on what's happening there. So I went ahead and created this derivative, and how I'm going to use it is the following. I'm going to go ahead and call this D output here. And what D output is going to be the air times the sigmoid derivative. And I'm going to go ahead and pass the output into that, because I'm calling this D output because it's the derivative of that output. And I multiply it by the air because the air is going to be kind of scaling this in the direction that we want. And then the next thing I need to do is adjust the weights. So what I'm going to do is I'm going to make the adjustment for weights 2, and this is going to be equal to the hidden layer. So that's the layer that we ended up passing into the activation function there, transposed times the D output. Okay, so what does all this actually do? Let's take a look at both of these values here. Let's take a look at D output, and let's take a look at the adjust weights 2. Well, I'm going to call this adjustment of weights 2 just to make it a little more there we go. All right, let's run this. And what we get are these values here. So this is going to be the output based on this derivative here, the sigmoid derivative, the air times that. And the adjustment of the weights gives me this really big value right here. And that's really way too big for us. We don't want to adjust the weights by that much. Now, it's okay to try to do this some of the time, but what it's going to actually end up doing is it's going to adjust it way too much one way, and then the next training example might time I run it through might adjust way more back the other way. So I'm actually like hopping over the minimum as I bounce back and forth, and by doing that, we actually will never get it trained to be the optimal neural network to give us the correct expected results. What we want to do is we want to kind of scale this adjustment down, and we're going to scale it down by something called the learning rate. And the learning rate is a value that we can change over time. And what I'm going to do is I'm just going to go ahead and set it to 0.01. And when I run this again, I'm going to get these much smaller values here. Now this might be too small. I might want to adjust it up a little bit, but I'm going to start it at this really low value just so you can see that this is about how much I'm going to adjust it by. And then we'll up it higher and higher as long as we can maintain accuracy. All right, now the next step is to do the exact same thing that we just did, except we're now moving from this hidden layer and we're going to go all the way back and adjust weights 1. So to adjust weights 1, we actually have to figure out how we adjusted these before we can figure out how we adjust this. And the reason for that is because weights 1, the changes in weights 1, will depend on the changes in weights 2. So everything's dependent going forward because weights 2 depends on weights 1. That means the same thing happens when we're going backwards. Weights 1 is dependent on weights 2. So if I adjust weights 2, then I have to go back and adjust weights 1 based on similar how much I adjust weights 2. So everything in the network is dependent going forward, and everything's dependent going backwards. And because it's dependent going backwards, and I'm doing the derivative in this case, this actually leads us to using the chain rule. And as I said before, I'm not doing the math here. And if you want to know the chain rule, once again, I'll say the 3 Blue, 1 Brown video series is excellent. They talk about the chain rule and how everything works. The goal, though, is not to get the calculus here. So what I'm going to do is I'm going to say the input in this case is going to be equal to the dot product of the output. Let's see, what do I got? Oh, okay. And the weights for self dot weights 2 dot transpose. Okay, and I'm going to multiply all that by the sigmoid derivative of the hidden layer. Okay, and I'm going to multiply that by my learning. Well, not actually quite yet. I'm going to get that. So run this. Let's get rid of this here. And let's print out D input. Give a little space. And I've got this here. So this is actually me working all the way back, really. I've got the weights 2 here times the output times the sigmoid derivative of the hidden layer is going to give me the D input, which I now need to multiply by these weights in order to get my adjustment of the weights. So D adjustment of weights 2, okay, adjustment of weights 1 rather, is going to be equal to the dot product of D input transpose times the D input. There we go. Sorry, D. What am I missing here? Yeah, that is input transpose. Sorry, that's what I did wrong there. Okay, so the input layer times the adjustment of the input layer. So if I run this again and I print out the adjustment of weights 1 and I print out the adjustment of weights 2, you're going to notice the difference. The weights number 2 is going to be, as we said down here, a 4x1 matrix, and this is a 4x4 matrix, which gives us 4x4. But once again, we want to adjust this by the learning rate. So all of these values get adjusted down a little bit. And we're going to adjust this learning rate up probably, but for the meantime, just keep it really low. And the last thing we need to do is take these adjustment values and we need to change our weights by those. So all we do is self.weights 1, okay, plus equal the adjustment of weights 1, and self.weights 2 is equal to the adjustment of weights 2. Okay, and that is backpropagation in a nutshell. So let's walk back through this really quick. So the first thing we do is we find the error between what we got from the output and what we actually are expecting to get. We then took that error and we worked our way back through the activation function by finding the derivative of the sigmoid, which means we're finding the gradient, which is going to tell us how much we're going to adjust each of these by. So this gradient value, if it's really high, that means the error value is going to actually adjust more because it's multiplying by the error. If it's really low, it means it's going to adjust that error. The error is really low, it's going to mean it's going to adjust it less. Okay, so it's going to adjust that based on each one, and then it's going to take that value and you're going to multiply it by what you got out of the hidden layer. Okay, and that hidden layer times that times the learning rate is going to tell you how much you're going to adjust weights 2 by. Now the second one is taking what we got. So it's actually working because of the chain rule. We have to take all of this stuff here and then we can adjust weights 1 by that. So we're doing the weights 2 times the output layer. Once again, we're doing all of that stuff there. Then we're going to go ahead and multiply that by the derivative of the hidden sigmoid, the activation from the hidden layer. That gets us back to this step where we find the adjustment, which is going to be whatever the this was here back up to this point before the hidden layer times the actual input. Then we get the adjustment for the set of weights 1. So that is a bit confusing, I'm sure, but the basic concept is find the error, find out how much we have to adjust the weights by, and then add those weights in. And we're going to do that again and again and again, but we're going to do that in the next video when we actually train the network and then check to see how well we trained it. Okay, so take a look down at the description for the additional material. Otherwise, I'll see you in the next video. Thanks for watching.